In this video tutorial, we're going to talk extensively about how to accurately calculate the avoided cost of a solar project, which is basically how much a project saves in dollar terms. Here's our agenda for the video. We're going to discuss average blended cost and average blended savings. Then we're going to model some real-world examples, and we're going to finish by demoing how to optimize for avoided cost. Average blended cost. Okay, so we're going to start with the basics and first principles and just start by talking about cost. So cost is very easily understood, and cost is simply how much is a customer's electric bill? How much are they paying? Now, we all know, depending on what type of customer we're talking about, residential, commercial, industrial, and the utility rate schedule that customer is on, cost can get calculated a number of different ways. We're going to talk about that later. For now, we're just establishing that cost is how much they pay in total. Okay, now let's talk about average blended cost. And this is actually also a very simple concept. And it's basically just expressing a customer's cost in dollar per kilowatt hour terms. So the formula for average blended cost is total electric bill cost divided by total kilowatt hour consumption. And in this video and in Energy Toolbase in general, we always express average blended cost in annualized terms. So it represents a customer's average volumetric cost over 1 year. All right, let's now jump in and demo how we calculate cost and average blended cost in Energy Toolbase. So as you can see, I'm on step 2 of the edit proposal screen. We're going to create an energy use profile, which is how we recreate an annual utility bill in Energy Toolbase. And as you can see on the options on the screen here, Energy Toolbase is really good with recreating utility bills based on whatever sort of data or file format you have your customers' usage in. We really specialize in working with interval data or green button data. So let's demo an example of that. We'll bring in an XML green button data file. I'm going to select a file that I've got saved on my local machine here and import that in. This file here has 1 year of 15-minute data, so about 35,000 data points in this file. I'm going to name it. I'm going to pick a specific utility. How about we start with San Diego Gas and Electric, and I'm going to pick a specific rate schedule in the SDG&E territory. How about the ALTOU rate, which is a medium-large commercial rate? And you can see all of that raw meter data being factored into our energy use profile table. And you can see in the bottom right hand of the table, cost or total annualized spend in dollar terms for this customer based on their interval meter data, and of course also based on all of the parameters that we've defined up top here. So for instance, this is all based on the August 1, 2016 effective date tariff. And for those users of Energy Toolbase, they're familiar with a lot of this, but you can also jump into the rate schedule details page and really granularly look at exactly how this tariff, the SDG&E ALTOU schedule, is defined. For instance, how the seasons are defined, how the time of use periods within those seasons are defined, and then of course all of the different charge types. Here I am in the Energy Charges tab. We're looking at over here on the right-hand side the summer season, on-peak, semi-peak, off-peak, dollar per kilowatt hour charges. You can also, of course, look at demand charges, fixed charges, or any other type of applicable charges for this schedule. And again, what we're attempting to do here is be really transparent when we recreate this bill, and in this case, tell you that this customer's total cost will be $51,486, and showing you exactly how we got to that math. Okay, now let's calculate the average blended cost. And to do so, we just have to save this. We'll go back into the edit proposal screen, and I'm going to navigate right to the bottom and the facility summary dashboard, and I'll just dock this open. And as you can see, we've already solved for the average blended cost, in this case 25.6 cents per kilowatt hour, which was the total cost, 51,486, divided by total kilowatt hour usage, 200,854. So this is a really useful number to be able to reference, the average blended cost. But be careful how you think about this number. This is not the same thing as the customer's dollar per kilowatt hour volumetric rate of energy. This is, again, the average blended cost. And in this case, the 51486 includes things like fixed charges and demand charges, which is why we're referring to this as an average blended cost. Average blended savings, aka avoided cost. Okay, so we've talked about cost. Now we're going to talk about savings. And savings and avoided cost can really be used interchangeably. And it's very simple. How much money in dollar terms does a project save? Or, which is the same thing as saying, how much cost in dollar terms does a project avoid or eliminate? So avoided cost is what Energy Toolbase really specializes in solving. And this is kind of the core competency of our software. So let's run through a quick example of how we calculate this number. And then later on, we're going to actually look much deeper and kind of unpack that. So here I am in step 4 of the edit proposal screen. Let's add a PV array. I'll use PV Watts version 5 as my modeling tool. And let's just throw in, how about a 75 kW DC rated system. I'll model this at a 5-degree tilt and a 180 south facing azimuth. I'm not going to change any of those system loss variables. Let's save this, which is basically generating a 365-day solar production file. And we can see this system is producing 114,473. And let's go right down to the cost, or the savings value. Again, the 51486 is the cost, as we talked about earlier. The electric bill after solar is coming in at 35,531. So the delta there is 19,955, which is savings or avoided cost. And now to express that number in dollar per kilowatt hour terms, or average blended savings, we're simply taking the 19,955 divided by the total solar production, in this case 114,473. And that's how we're deriving the 17.4 cents a kilowatt hour blended savings. So to quickly recap what we just did, the formula on average blended savings equals total dollar savings divided by total kilowatt hour production. And this blended savings value represents how much the solar is worth in dollar per kilowatt hour terms, or how much cost is avoided in dollar per kilowatt hour terms. And this is a very useful number to be able to reference, as we'll look at more deeply in a minute. This value really encapsulates the value of solar for a specific project based on all of the defined project assumptions on that project. Blended cost does not equal blended savings. So very important concept to understand, that blended cost does not equal blended savings. These are two very different things. Again, the formulas. Average blended cost is total utility bill cost divided by total kilowatt hour usage. And average blended savings is total dollar savings divided by total kilowatt hour production. So again, in this basic demo project that we set up, we can see there's a pretty significant differential between these two numbers, 25.6 and 17.4. So if you're a solar salesperson and you're presenting analysis to a customer, assuming that the blended savings is the same thing as the blended cost, shame on you. You know, in my opinion, you are lazy and ignorant at best, and unethical and dishonest at worst. Because generally speaking, what you're doing when you're making that assumption is you are overinflating the savings of the project. In our example here, you would be telling your customer they're saving a significant more amount of money, 25.6, as opposed to what they really are, 17.4. Okay, so I think a good way to illustrate the point I just made is to run through an example of a power purchase agreement. Because pretty much everyone in the solar industry knows that for a PPA to make sense, it's got to save the customer money in year one. And a pretty well-known industry target is 10% savings in year one, which is basically saying the cost of the PPA energy is 10% lower than what the customer would otherwise pay for the utility for that energy, which makes for a compelling value proposition, and likely a salesperson could sell that project. Okay, so I'm in step 6, transactions of the edit proposal screen, and I've already set up a PPA, and we can see I've got a 20-cent starting rate, 2.5% escalator, and 20-year term. So pretty straightforward set of assumptions on the PPA. Let's jump now into a proposal document and talk through the point I was making earlier. So let's go right to the project summary page. And again, we can see those same assumptions that we've set up. And just as a recap, the average blended savings of 17.4 cents a kilowatt hour and the average blended cost of 25.6 cents a kilowatt hour. Okay, let's jump down to the cash flow statement where this really becomes clear. Now, the PPA payment of 22,895 is a function of the 114,473 at a 20-cent starting rate. And as we know, the electric bill savings of 19,955 is that 17.4 cents average blended savings value. Here's where you could go wrong. If for the savings piece you were using the 25.6 cents average blended cost value, and you're going to say, okay, it's 25.6 times 114,473, my first year production, great. I'm saving my customer 29,300 and change. And this deal is going to be well in the money, right? They're paying 22,900 in PPA payments, and I'm saving them 29,300. Great, this deal's $6,000 in the money year one, and it's just going to get better and better. Well, that's the point I really wanted to make, and that would be a gross misrepresentation of savings, or average blended savings in this case, based on everything I've explained up until this point. Real-world commercial example. Okay, so now let's dive deeper into some real-world examples and demonstrate how the avoided cost or average blended savings of the project changes when we change different project assumptions. So we've got that same deal that we've had set up earlier with an average blended cost of 25.6 cents, an average blended savings of 17.4 cents. Let's start in step 2 and toggle a rate switch. So all of this math was originally run based on the assumption that this customer was on the SDG&E ALTOU rate, and they stayed there after the solar project. Now let's toggle this to the quote-unquote solar-friendly rate, which is the DGR schedule. And you'll also notice here we offer the user the option to either force the customer to the new schedule or choose the rate with the greatest savings. Let's force them to the DGR, which I know is a better rate generally for commercial developers. And there we go. As we save that, we can see that average blended savings value really significantly increase all the way up to 22.3 cents a kilowatt hour. So thinking back to our PPA example, all of a sudden now, if we had a PPA starting at 20 cents a kilowatt hour, this deal is in fact in the money by 2.3 cents in that scenario. All right, so let's keep adding more layers to this same analysis. So while we're in step 2, let's set up some net metering version 2.0 assumptions. So I'm going to go into the additional details and into the metering type hyperlink so we can configure any sort of NEM 2.0 assumptions. And a quick side note, I actually just recorded a pretty in-depth video on net metering version 2.0 that you can reference and get a really deep dive on what all of this means. But let me just jump in here and assume this project, which actually is in fact true in SDG&E territory now, has non-bypassable charges of 2.5 cents a kilowatt hour. So let's jump out and now save this and look at what that does to the average blended savings, now going down to 21.7 cents. And this is effectively just discounting exported energy by 2.5 cents in this example. And as we can see over here on the right, the amount of energy being exported based on this customer's load profile and the solar production and design factor we set up in step 4 is going to be about 21% of their 114,473. So again, we can see the combined effect of a rate switch and NEM 2.0 assumptions on that average blended savings value. Okay, let's keep having some more fun here and change some of our system design parameters on the solar side. So here I am in step 4. And before I do that, let's reference again, currently we're producing 114,473 kilowatt hours first year of production. And some folks like looking at that value in terms of kilowatt hours by kilowatt, and that's 1526. And this is all again based on using the PV Watts version 5 API in a system at 5-degree tilt, 180 south. So let's change this to something really extreme. How about I go 15-degree tilt, and I'm going to face this due north. And as I save this, all of our numbers are going to re-update, including that average blended savings number. So this is really interesting now. The solar production went all the way down to 94,187, or 1256 expressed in kilowatt hours by kilowatt. So that went down pretty significantly. But the average blended savings, or the value per kilowatt hour of solar production, actually just went a little bit up, right? Now at 22.3. So again, another consideration as we change variables, especially on the solar system design side, also has a direct effect on that avoided cost or average blended savings value. All right, I've got one last change I want to throw in to illustrate a point here. So remember, all of this math is based on the customer's unique load profile, both average blended cost and average blended savings. And if we want to take a really quick look, let's jump into the analytics. Let's go to the demand profile visualization. Let's actually just look at the usage side and just kind of zooming in. This looks like a pretty typical looking office building load profile, coming in at 6 or 7 in the morning, leaving at 5 in the afternoon. You can see the Monday through Friday, pretty consistent shape of that load profile. Midday user. Okay, now let's swap in a different energy use profile. And I've got an extreme example set up here to kind of prove a point. So I'm going to save this. And I intentionally set this up so that we have the very similar amount of usage, 200,854. That's actually identical to the profile we were just looking at. And we're on that same utility rate schedule, the SDG&E ALTOU. The only difference really is the customer's distribution of their load. In other words, they use the same amount of energy. They're just using it at different times over the course of the year. And you can see that massive extreme difference down there in the average blended cost, jumping all the way up to 56.3 cents a kilowatt hour, which is actually real math. And let's just jump into the visualization screen to kind of eyeball what's happening here. And this is that load profile, again, that over the course of the year uses the same amount. But you can see this is just really pretty extreme with how spiky that is. And oftentimes, even on weekends, there's actually zero load. So this is, in fact, real data and a great illustration of how dramatically the load profile can change the average blended cost. But look at the savings value of 16.7. Actually really didn't change that much. Let's just quickly run through and kind of change some of these toggles again here and see how these update. Moving to DGR. Wow, really radical change, 16.9 all the way up to 69 cents a kilowatt hour. Again, extreme example. A lot of this has to do with the change in the solar-friendly rate and the fact that so many of those demand charges on the ALTOU schedule are being reshifted into consumption-based charges. And again, same applies. We can add additional layers. And let's go back to a NEM2O 2.5 cent NBC model. This probably won't change all too much. 69 cents down to 63. And again, changing other types of assumptions about this project. We can see instantaneously the effect. How about we make this ideal again? Let's go 15,180, which I would expect to increase the solar production yield, currently 94,195, going back up to 121,000, but significantly reducing the value of that solar, now down to 56.9. So a lot of illustrations of the different assumptions and inputs being toggled, which are going to drive the average blended savings and average blended cost calculations. Optimizing avoided cost. So I now want to demo how we optimize the dollar per kilowatt hour blended savings of a project in Energy Toolbase. So I reset everything back to our initial set of assumptions. Again, we had a office building load profile. We're rate switching between the SDG&E, ALTOU, and DGR schedule. I've got some NEM2O assumptions valuing non-bypassable charges here at 2.5 cents a kilowatt hour. Moving over to step 4, we can see we're using the PV Watts version 5 API. This is for a 75 kW DC rated system at a 5-degree tilt, 180 south, no shade, and default system loss variables. So I know that's a mouthful, but those are all of the variables that are factoring in, again, towards the average blended cost and average blended savings value. Okay, let's now access the ETB optimizer, which is in the bottom of step 4. And the chart on the top left is the blended electric bill savings expressed in dollars per kilowatt hour. So for those of you that are seeing these charts for the first time, here's a real quick kind of overview. The x-axis is the DC kW power rating of the system. The y-axis is the dollar per kilowatt hour blended savings. And then you can see down there in the legend the 2 rate schedules we've set up, in blue ALTOU and in green DGR. So here's how this works. As we hover our mouse on this chart, we're actually showing exactly what those avoided cost in dollar per kilowatt hour values are for each respective system size. This chart, the 40 kW level, is really kind of standing out for me because that's where those 2 lines cross. In other words, a system smaller than 40 kW is actually better off on the ALTOU schedule, and a system greater than 40 kW is better off on the DGR. They're getting a higher dollar per kilowatt hour blended savings value. And as you can see, as we go up higher on the chart here, that differential really kind of starts to widen. One thing I do want to point out, though, is high on the chart, if we just now look at the DGR, right around 118 kW, we can actually see a little bit of a fall off. So here's a really cool feature within our optimization tool. I'm going to click my mouse, hold, and hover, and kind of resimulate between a 105 kW and a 131 kW DC rated system. So you can see that resimulation just ran. And let's again just have the DGR up on the chart. And now we can really definitively see where that fall off occurs, right around 120 kW, right? As we build a bigger system, the blended savings value is really falling off pretty hard here. So this is being caused by the fact that at the end of our 12-month net metering cycle, this customer has dollar credits. They have a balance of dollar credits in their energy category. So at the end of that 12-month true-up cycle, they actually lose those dollar credits. And again, the big takeaway here is that 120 kW really is the optimal size system if we're optimizing for, again, dollar per kilowatt hour blended savings. So this is a quick illustration. Hopefully you can start to appreciate the power of the ETB optimizer because really all of this analysis is based on all of those parameters that we've talked about earlier. Load profile, system design, rate schedules, etc. And this really allows you to model different types of scenarios and solve and optimize for that dollar per kilowatt hour avoided cost value. Thank you for taking the time to watch this video. It is very important to accurately calculate how much money a project is going to save before you present analysis to a customer. So regardless if you're using Excel or Energy Toolbase or any software program for that matter, I personally believe solar salespeople have a moral obligation to do this math correctly. You're welcome to contact us with any questions or comments, and you can check out a free trial of our software at energytoolbase.com.